So let's look at a couple of examples of the Nernst equation. The Nernst equation. Remember, we use the Nernst equation to find the voltage of a cell at non-standard conditions. Now the degree sign tells us the standard voltage, and that's based on ions being at 1 molar concentrations, gas pressures being at 1 atmosphere if a gas is involved, and temperature always being at 25 degrees Celsius. So when we take this one, the zinc and copper electrode, first of all, and just to get more practice in on all phases of this, let's analyze what's going on here. Zinc on the reactant side is the solid, and it is turning into the zinc ion on the other side. That means it is being oxidized. So it's the anode. So we'll have zinc solid becoming zinc ions in aqueous solution as our anode on the left side in cell notation. Then we'll do the double vertical bar here to represent our salt bridge. And on this side, for the cathode, we'll have cupric ions in aqueous solution, cupric copper 2, becoming solid metallic copper with a 0 charge. Okay, anode over here, oxidation, cathode over here, reduction. All right, the standard voltage for this cell, is going to equal the reduction potential, standard reduction potential of the cathode minus the standard reduction potential of the anode. We'll look those numbers up. For our cathode, which is over here, we find that if copper 2 gains 2 electrons to become metallic copper, that's 0.34 volts. From that, we're going to subtract the standard reduction potential of our anode. Now, it's going to be written backwards in the table. It's going to show zinc plus 2 electrons, zinc 2 plus 2 electrons forming solid zinc. When we look that up, it is negative 0.76 volts. So we put positive 0.34 minus negative 0.76. We get a standard electrode potential or cell potential for this cell of 1.1 volts. So our non-standard potential will equal that standard potential of 1.1 volts minus 0.0592 over N. Now what is N? N is the number of electrons being exchanged. Zinc is losing 2 electrons to become plus 2. Copper 2 is gaining 2 electrons to become solid elemental metallic copper with no charge. So the number of electrons is 2. Next we need the log of Q. So we have to go back to our problem here, and what it tells me is for this example, if I can find it again, look here. So in this problem, it stated that the zinc ion concentration was 1.9 molar. Hope you can read that. Yeah, 1.9 molar. And the cupric ion concentration was 0.1 molar. So what is Q? We're going to take the log of Q. Now Q, like K, is a fraction. What goes on top? Products go on top. Which of these two ions is a product? Well, the zinc ion is the product, so that's 1.9. And the cupric ion is here on the reactant side, and it is 0.1. All right. So 1.9 over 0.1 is 19. And the log of 19 is, there you have it, the log of 19. 1.9 over 0.1 is 19. The log of that is 1.279. 1.279. We multiply that times the 0.0592 over 2. So we're going to multiply that by 0.0592. We're going to divide that by 2. We're going to get 0.038. So we're going to say minus 0.038. So it's 1.1 minus 0.038. And that'll be 1.062. Not a huge difference in that particular example, but that is the way it would work. Okay. Now let's do another example. Okay, so for this example, we have the cadmium cell, the lead and cadmium cell that we had looked at earlier. In fact, here are the calculations we had done earlier. The cadmium reacts with the lead 2 ions to produce cadmium 2 ions and lead. There's the cell notation. This turned out to have a standard cell potential of 0.27 volts. Okay, so we'll bring that with us. Standard cell potential for this was 0.27 volts. Okay, so notice that it is not at standard conditions. The cadmium concentration is not 1 molar. The lead ion concentration is not 1 molar. So we're going to use the Nernst equation. All right. So our actual potential, the actual voltage this cell should produce, will equal the standard 0.27 volts minus 0.0592 over N. Once again, N is going to be 2 because cadmium is losing 2 electrons to achieve a +2 charge. Lead 2 is gaining 2 electrons to get a 0 charge. So this will once again be 2. And then we're going to need the log of products on the top. The product ion is the cadmium, so that's 2. The reactant here, we go from reactant to product at our cathode, is 0.001. Okay, so 2 over 0.001 is 2,000. And the log of 2,000, you can do it with a calculator if you like, but it's 3.301. And that'll be multiplied by 0.0592 and divided by 2. And the result of all of that will be subtracted from the 0.27. So I'm going to pause and calculate that. So when I said for the log of 2 over 0.001, which is 2,000, I get 3.301, multiplied that by 0.0592, divided by 2, I got 0.0977. All right. Now, we were working with 2 decimal places over here, 0.27. So if I try to subtract 0.09 from that, I'm ignoring the 7. So this 77 makes that 0.09 round up to essentially 0.1. Okay? 0.0977 or 0.098. Well, that's 3 decimal places. I've only got 2 in my standard calculation over here of 0.27 volts. So 0.098, I'm going to round it off to 0.1, giving me a voltage for this cell at non-standard conditions of 0.17 volts.